All right, good morning. So welcome to Calc 2. I see a lot of you guys have started on your homework already, which is fantastic. And what I'm going to do is I'm just going to try to do some lectures to kind of guide you through the chapters and see what we. So what I'm going to do is I'm going to go ahead and share my screen here. Just see the tools I'm going to say. Control calculator. You guys are quite invited to calculate. It's fine. Add here. It's too much. This way. So let's get started with doing chapter 7.1. Today we'll have to make sure that you guys had a review. Suspect that everybody's Calc 1 was worthwhile, but at the same time, and this is even without COVID. Those students watching maybe feel a little under prepped for being in Calc 2. It's kind of scary. Okay, so what do we have here? We're talking about irrigation. And pretty much what we're doing, at least at first, is we're talking about. So think to myself, like, well, what if we have our alphabets here is equal to squared 7, right? And I take my derivatives. So we're going to just use the power rule. The 2 is going to come in 5. Right? 2x, and then the exponent decreases by 1. And then the derivative of the constant, right? That's just 0. So we're done here. And g of x, right? This is, we'll say this is equal to x squared minus 1. So g prime of x, right, is equal to, again, take the derivative. It's 2x, negative 1 is a constant, so this equals 0. So here are my two functions, right? Now, the goal for chapter 7 is we're going to go backwards. Here's the problem. It says, well, what function gave us this derivative? And what we're going to do is we're going to say, well, this is the power rule, right? X to the n, right? We're going to get x to the +1 over n plus 1. So this is going to be 2x to the 1 plus 1, so 2 here. So we're going to be 2, right? So this is 1 plus 1. And 5 are the same thing. The 2's cancel and we get squared. Okay, well, what about this one? What if I wanted to take the g of x? So what's going to happen is we have 2x. So that's going to be 2x to the 1 plus 1 over plus 1. So it's going to be 2x squared over 2, and so we get squared. Wait a minute. We started off two separate functions there. When I took the antiderivative, like, shouldn't I end up with two different functions? Well, yes or no. The problem with derivatives is that constants look a lot like zeros. Like once you've taken a derivative, constants that were there, they're lost. We don't have those anymore. I can't like extract something from a zero. I can, but it's real fuzzy, and I don't really know what it's like. So to combat this problem, we're going to do a C here, plus a constant. So if I say the antiderivative f of x or g of x, or I shouldn't say that, f prime g, let's go with that, is equal to x squared plus some arbitrary constant. Well, if I plug in 7, I get back to f of x, or when I get back to g of x, we might need some additional information, definitely some additional information to decide what the value of this constant is. But that does fulfill the conditions that both of these anti-derivatives now will solve and will be solutions for the same function. Okay, so this answer will serve for both of these solutions to both of these. Like I said, if you need more information, you can see some problems are going to include that. But that's pretty much what we're doing. That's why the C is there, and that's kind of so. Let's see here. I have some other thoughts on this. The derivative. I take the integral of f plus or minus g. Then we're going to end up with f of x plus and of g of x. And this worked exactly the same as it did for derivatives, right? If you had to take the derivative x cubed minus the square root of x, x to the 1/2, plus x to the -2, right? You wouldn't think about taking this derivative. I've got to figure out what the whole function is. You wouldn't do it, right? You would just go ahead. You would say the derivative is here. Careful. We're all going to make that mistake a couple of times. It's part of for two is we kind of go backwards and forwards. So this is 3x squared minus 1/2 x to the 1/2, right? Half down in front. Say 1/2 minus 1, right? So if you have 50 cents and you spend $1, you're in debt 50 cents. It's going to be minus, right? So -2 comes down. And then we subtract 1. So you're $2 in debt, you spend $11. So that's what the derivative to these term. Well, if I wanted to go back, we'll take integral of this previous function. So what we're going to do is we're going to say, well, that's just going to be 3x to the 2 plus 1 over 2 plus 1 minus 1/2 x to the -1/2 plus 1 over -1/2 plus 1. And this will be minus 2 x to the plus 1 over 3 plus 1. Right? And if this is where you are right now, but you're not doing it in the better way. Look, let's take COVID. I think okay. So that's 3 over 3. Gotta put that in there to keep yourself reminded. That's fine. I did this for a long time. Fractional exponents, just because it was kind of hard to keep them straight. 1/2 plus 1, that's 1/2. And that's 1/2. These halves are going to cancel. So we have 1/2 per half. Plus, we could do 2 here. So like 2. -3 plus 1 is like 2. -3 plus 1 is like 2. And then we know what the original answer was, right? So here we go. I simplify this out. X cubed minus x to the 1/2. The 2's cancel, so we have plus x to the -2. C and the original function here, g of x, pretty much ended up the same. Except that here, 0 is a number, that's fine. I didn't have it, it's the term, but that's fine. This goes back to g of x. So that's how the derivative together here. Operations, kind of like squares and square roots, or his favorite logarithms and exponents. So that's the relationship between those. Let's see here, a couple extra rules. Have the x. This is the easiest integral you'll ever urge to do. or integral of x is e to the x plus c. It gets a little bit harder to get to this bit. I'm only including this one as the book is here. The fact that it's here because what if you didn't memorize this rule? Like, is life over? Is it 7 foot? As far as I go, 7. Now 7.2 will show you different. Okay, so if this is a tough rule for you, 7.2, and actually that is true for everything. If we want to integrate the x, so this is x to the negative 1 x. Now the problem is when I go to integrate this, by the way, when I integrate with the triple sign x, they both go away. So these kind of work as a catalyst, right? This is like the catalyst to help the action go. So when you integrate, this gets used up, this gets used up, both get used up. So we're going to end up with x to the negative -1, negative -1. See an issue yet? So it's not going to work out. So we have a different rule for this particular function. And the rule is that this is equal to the natural. So how do I use absolute values? Well, if I wanted to integrate, say a function like this, if I wanted to integrate x squared, this is what x squared. That's what x squared looks like. I'm not going to, anything I integrate, or x cubed, I can put any number I wanted here, put it into here, and it'll be just fine. If I have 1 over x, right? 1 over x looks something like this. It's 1 over x. So when I integrate this, like, and I've got numbers over here, say I want to integrate, between here and there, we end up with natural log x plus c. Now, if I'm integrating where it's negative, go ahead, put in the negative x. Okay, let me know what happens there. It's a natural log, and I put in a negative number. Then it goes, that's all. Can't take the natural logs and negative. You're going to need complex to do that. We're not getting in there for it's here. So let's take the natural log and negative 5. It's not really. So that's why we put the absolute value in there. So it have a negative 5. We still get an answer. So I could be natural log of 5. That's fine. 5. That's going to give me. But if I put a negative number in, so what about 0? Is this function designed at 0? Is it 0? Now, at 0, it's not. So the fact that the function doesn't really have a value at 0, the integral is also not value at 0. And get into what happens when you integrate something like this. That's chapter 8. Okay, so that's why you need the absolute values, but you don't always. Okay, like I ended it with x squared or 1 squared plus 1. In this case, if you end up with like a natural log, x squared plus 1 is this will never be a negative number. X squared plus 1 is never negative. So you don't need the absolute values if you know that here it's always going to be positive. But if you don't know, then put the absolute values in. I promise you it's not nearly as intimidating as it may be. everybody's experience with absolute values is like this global experience. I get that, but eat it just in case there's stuff that you. So don't be intimidated by it. Actually, if you're going to have to deal with that, you're going to have additional information. You're going to know x is less than 0, so we need. Or you're going to know x is greater than 0, so we may not need. So just be aware that you need to put them in if you don't know what else is going on with the problem. But you're going to be evaluating things. You're usually going to have some additional stuff to know. So we also have rules talk about a to the x, and let me show you this one again. There's a fact that it's sitting there. To be honest, the x is the one you have to remember for the rest of your life. This one, they teach it to the engineering kids too, same way. But they expect them to memorize this formula. And quite honestly, I have never this formula. So the way I do it is, do you remember a technique of to the natural law of something to the ln of 2? With second function e, right? That's how we get e to the natural law of 2. Right? We end up with 2. Seems awful. I wonder if it's a good coincidence. Pick any number you please. Okay? Any number you like, 20. Let's not do 20, let's do 30. Maybe it has something to do with 2's, right? So I e to the natural log of 30. So 2 like that's how natural logs work. That's how the exponents in the natural log function are. They are inverses of each other. So when you have e to the natural log of a, that's equal to a. Here's an a. So here we have here to the natural log of a times x. It's about or so. We have this one, e to the kx. This was 1 over. This is k, right? And this is e to the natural log of x. Just like the formula right here. K, e to the kx plus c. So we're here. So let's see. So the integral a to the x, this is 1 over 2 log of a, e to the natural log of a, x, c. Now, our rules of logarithms, so this might help, this might not help. This is e to the natural raised to the x. Okay, so when you multiply, right, in this format, when you multiply a to the r to the s, that was a to the rs. Go backwards too. That's what I did here. So backwards. So this just turns into a, right? So this is 1 to a to the. That's how I memorize that formula. That's how I use that formula. And it doesn't happen often. So like warrant space in your head to have this memorized. Logarithms are important. These are important. So it does make sense to use it to have this kind of stuff memorized. So you have rules of logarithms and properties of logarithms. But this just doesn't happen. Calculus will like e for obvious reasons. Derivatives and and harder. Okay, let's do some examples. Let's do 7.1 examples here. So let's see, and let's just start. So squared minus 6x is 3. We want to integrate this. Like I said, at the beginning of this, if you're, if this is where you are at the beginning, it's fine. You're going to get better. So it takes a little bit of practice, but you are going to get better. So this is 5x to the 2 plus 1 over plus 1. If you want to, we can even say that we integrated 5x squared minus integral of 6x plus 3. So what about the c's? Well, let's put them in. So we have a c1 for this integral. Minus 6x. I'm going to go ahead and just put the 2 in. Okay. But we have a, how about c2? Okay. Integrating c, or 3 rather, this is 3x to the 0. When I add 1 to this, right, we just get 3x over 1. That's how that's working. 3x. And then we have plus c. What's a constant? Plus a constant, plus a constant. It's a constant. So what we could do is we could wrap up c1 plus c2 plus c3. Just say, well, it's going to combine them all. Step here. It's a minus. So, plus 3x, right? 6 over 2 is 3, and we have our 3. And then this is c1 plus c2 plus c3. We're not going to keep track of all of that. We're just going to call it c. Because a constant plus a constant plus a constant is, in fact, a constant. So that is going to be our answer for this one. I would tell you that in definite intervals, doing this, your C is an automatic one reduction. So, regardless of what your grade was, I only graded our 6 points. So, it's a 1 point reduction. It's a 1 grade reduction. So, if you got the right answer, got your C with an A and an A. Okay. A little mistake in here, it's not a B, it's a C. So, you have to remember this. But about something that's a little harder. So what if we have t to the plus pi to the 1/5 integral dt? Trying to trick you here is what I want you to do. So this is going t to the 4th plus 1. It's a fancy way to write 1 but well, 1. Now, plus pi to the 1/4. Pi, you're trying to trick you. This is exactly what it's trying to trick you. That's a constant. So this is some constant, and we're integrating a constant. That's always going to be a t(c). So regardless of what this looks like, it's square root, quarter root, whatever. It's still just a constant. Or t, because it's t to the 0. C. So 1/4 plus 4/4, so it's going to be t to divided by plus pi to the 1 t plus c. Right? Now, we're not going to do this. This is a compound fraction. What you're going to do is you're going to, this will cancel. 4/5 will cancel with 5/5. 4/5 t 4ths plus pi quarter t c is our answer for this. Let's try one. So squared to the fourth, 4x times 3. All right, here is one of the biggest errors that students will make. So be really careful not to make this mistake. We have a rule for plus, right? We have integral of f of x plus g of x means we do this, separate them out, and integrate each one separately. Plus or minus addition or subtraction. We do not have a rule for multiplication. That's 8.1. Just like when you wanted to take derivatives, right? We had a product. You guys remember having to memorize the product rule? Don't forget. Or quotient. We had to go back to do that. Product rule had some things. So integrals are a little bit trickier than derivatives. Why do you think this is going to be easier? So what we have to do in this case, because we don't have that rule just yet, we have to multiply through. So this is the same thing as x to the 2 plus 4, that's 6 plus 4x 3, 2 plus 1, 8, plus 3x squared. Don't let them trick you. Don't let me trick you. Where this? This is going to come up over and over and over again. Why now? So, I've taught this before. And you think, well, it's the pandemic. No, it isn't. You're in the same boat. So don't belong here. Put yourself up for being a little bit tricked by this, but don't be tricked twice. So that's 1/7 x to the 7 plus 4 x to the 4th 4 8 squared 3 constant. So why did you write the 7 over the x like that? You could have, it's fine. Like 1/4 of something is the same as that, like 3. Okay? 1/4 of 3 is the same as 3/4. So either way you write it, it's just this way. I'm writing what is 1/4 of $3. This way I'm writing 74 cents. So it doesn't really matter where you put the fraction like this. If it's directly under, that's fine. If that's front, that's fine. It's not going to be. So it's 1/7 x to the 7 x to the 4th x squared c. Generally, if they're going to cancel, I'll usually write them this way. Just think this looks easier. 1/7 x to the 7th. To me, it looks a little less intimidating. And you might feel opposite. You might, I'll just wrap it up in a nice package. I like this instead. Okay, I'm not going to argue with you. They're both good. So there we go. Let's do one more here. Let's do square root of x plus 1 over the cube root. So the first thing, right, we taught you rational exponents in algebra for this reason, because this is a nice algebra problem. This time calculus something. So what I want to do is I want to rearrange this. So this is, how do I write x to the, the cube root of x, right? Isn't that x to the 1/3? But it's in the denominator, so we're going to go ahead and exponent times x square root is really 1/2, isn't it? It's 1. Now, if any of these were like on the outside, like this is 1/2 of it out here, we could not do this trick. It's got to be on the individual exponents. What we're going to do is we're going to flip this. We're going to multiply it through x 1. So remember what the rule is for the exponents, right? Multiply the bases, we add exponents. So here we're going to have to think x 1. I'm sorry, 1/2 minus the 3rd, right? So we have to get common. So we have 3/6 minus 2/6, which is 1/6. Okay. So this is going to be 2/6 plus x to the negative So remember, if you think of like, here's my reaction, and to help my reaction along. So let's go ahead and integrate. And here's a time when I was like, not really that good with adding fractions, so I'm going to go ahead. So let's go on here, so I don't lose the parts. This is x to the negative third plus 1, plus 1, 6. Well, you might need a little bit of help here, right? One is really to the 1/6 plus 6 over 6. 6 plus 6 over 6 plus x to the negative third plus 1. Negative third, so 5 thirds. And I will go faster, so if you're looking, it's like, this seems a little slow. And is it patronizing us? No, I am. Just know that for a lot of students to take this class, there are some gaps and some holes in what they're good at in math. And I'm just trying to make sure that we fill in some of the holes before we to the goal. That being said, if you're having trouble with this, I want you to tell me, hey, I need some refresher on some fractions, or I need some refreshers on this. Because I want you, I want to fill those holes in and make it so that it's the class we can have it suffer with it your life, never have a chance to fix it. Honestly, I had a student who this class during the before times, she confided in me, she's like, I failed this class twice before. This is because I don't know how to do fractions. She came to my office hour. Fractions, I don't people. I don't think you feel bad for not having. Like, let's just solve that problem. Get you up to speed with fractions. Get you up to speed with a skill you don't have, so you can pass this class. That's where I'm thinking. So it's not meant to sit there and show how good I am. Show how good you are. And I remember her. I remember the fraction thing. She spent a lot of time stuff. But she was one of my better students. I mean, she ended up with a class with an A, finally finished it, got her degree, and left for better things. So I only remember that she didn't know the fractions because she said so. And then she came to my office like every night to work through it. And then she did really well for class. But for the most part, I'm not going to remember states that just a fraction. I'm not carrying that around with me. You shouldn't either. Not everybody had great math. Not everybody was ready to hear it when they taught it. Okay, it's fine. Let's see. I'm going to do 2 more. 61. These are the word problems. So we have g of x over x. To show here. So a model describing the population of adult flower beetles involves evaluating the center. G of x is the per unit abundance growth rate, population size. So this is the marginal. This is the rate of growth that they're talking about here. And in this case, we're going to say g of x is a minus b of x. They got to tell us this stuff. Otherwise, remember, you can't just integrate. Got to use a rule. They don't know that. If they're going to tell us this, they got to tell us some more stuff. So we're going to keep them. This is find the integral in this case. So what do we have? We have a plus bx over x. This is easier than the problem we just did. This is a over x, or a times 1 over x. And then b, right, that's just going to be x. That's all. You can do this with the top. You cannot do this with the bottom. Okay. So if I've got $1, I could say that I've got 4. We could say that that's 1/4 in 1 and 3/4 in 1. Okay, I've got $1. I can't say, well, let's go ahead and do it this way. Let's say this is going to be 4/3, or even, right, something like that. 2 and 2. You can't do this, right? We have 4 quarters. All of a sudden here I'm saying I have $2.67. Now I can't magically turn my $1 into $2.67 just because I took the quarters in front of the buckets. Like, that would be great, but that's not how it works. So if it's on the top, yeah, you're allowed to separate it. So do you remember what the rule was for one of those? So we integrated, push that up. So this is A times log X plus B X, because that's the other integral, they're a constant. Now, what the heck is X? For X, we're talking about population of size X. So here's where you can get away from those absolute values of some context. We are going to have a negative population size of beavers. I'm sure some people would really like a negative population of beavers. Don't have negative population. We're stuck with, we have at least 0. I don't see a flower beetle, so the worst I can do here is 0. But even that, we can't put 0. Then you need mommy beetles and daddy beetles to make more beetles, right? So we can't have 0. So since we know that X is the population, we give you something like A, L of X, B of X, C, this is our population, and we might put back here, X squared 0, simply so that you have to have positive numbers. Then you don't have to deal with the absolute value. That scares you. So, like I said, what times, if it's just a drill problem, that's all. Okay, it's a drill problems. Drill VR. I think drill. But when you have context problems, we have story problems. There's a context to it, what these variables mean, and say something like, no. Now, if it was a temperature, probably model for a temperature because things can be at 0. But things can also be negative. So we would have to maintain absolute values there. So that's how you interpret stuff like that. And in my experience, most of the students that take this class are either chemistry or biology or something like that. It is rare for business people to take elements of Calc 2. So my choices to pick problems, especially for like and such, word problems, is something on the science side of. I'm not saying it can't ever happen, but we're gonna. I tend to choose the science problems simply because that tends to be your majors. So I'll look at 70. So you have distance, right? Now, here's our acceleration. Here's our acceleration. Acceleration, A of t. Now, in planet Earth, in this universe, we tend to have constant accelerations. There are times where that's not going to be the same, but it's usually like the forces on something are getting bigger. So if you have like a black hole that's accreting, then that would be something that would be. That would be something that should happen. This is usually not efficiently had. Actually, anytime you go in a circle, you have acceleration that is a constant. So roller coasters do not have constant acceleration. Airplane, not going to have constant acceleration. So we have 18t plus 8. So we have A of t. This is 18t plus 8. They also tell us the velocity after 1 second. velocity after 1 second is 15. And distance after 1 second, rate S's look like 5, so I use a script S. Velocity after 1 second is 19. All right, so we know that velocity, if the derivative of velocity is acceleration, so velocity is equal to acceleration. So the velocity integral of A of t is going to give us velocity. And since in the end we're in a position, so find S of t under position I. So we have so this is going to be v equals integral of tt 8 t, right? And then this is not so bad of an integral, is it? It's going to be t squared, right? Exponent, right? Plus 8t plus our constant. We're going to have to do this again because position is the integral of velocity. So, but we also know that at 1, v is 15. So when t equals 1, v is 15. That is equal to 9 times 1 squared, 8 times 1, c. So it's 17, right? 3 plus 8, 17. 15. Subtract 17 from both sides. Minus 2 is equal to c. You sure it could be negative? We think friction is movement. So yeah, this is one the back of the brake on. So my velocity function is going to be 9t squared plus 8t still. And now we're going to get our position. So it's equal to, right, the integral t squared plus 8t minus 2 to plus. So we're going to have t cubed 3 plus 8t squared over 2 minus 2t plus c2. And what do we know about position? Added. It's right here. Said that when s at 1 second, s was 9. So at once, let's clean this up. This is s of t. So s of t is equal to 9 over 3. So 3t cubed, 4t squared minus 2t c. And we said when t equals 1, that 19 is equal to 3 is 1 cubed, which is just 1, plus 4 times t squared, which is 1, plus 2 times 1, c. So here we have 19 is equal to 3 plus 4 times 2, c. If I didn't know any better, that was 5. 3. C is equal to 15. So my position rate is 3t cubed plus 4t squared minus 2t plus 14. There we have it. So that's what they want. That's what they want us to do. So I'm going to go ahead and leave us there. Try to put up some 2 today and some someday. So thank you. Bye. Get to it.